Okay, hello, welcome back to CS492A in fall 2024 at KAIST. Unconventional computing is our topic, but first, let me announce that today and tomorrow is KAIST Post-Tech Science War, right? And in order to encourage and facilitate your participation in this KAIST Post-Tech Science War, we're going to not count attendance today. Let me say it again. Attendance today does not count. And as usual, I'm going to record this lecture. So if you miss today's lecture, if you're absent from today's lecture due to KAIST Post-Tech Science War, then you will easily be able to catch up by watching the recorded lecture online on YouTube. And those of you who prefer to attend and watch this lecture in real time are, of course, more than welcome to do so. So last time I mentioned two important things that every student who graduates from KAIST is supposed and is expected to know. First thing, every student who graduates from KAIST should know at least one proof that there are infinitely many prime numbers. There are many proofs, it's famous, and people come up with new proofs all the time. I know like 5 different proofs, but a student who graduates from KAIST, I think, should know at least one proof that there are infinitely many primes. Second, any student who graduates from KAIST should know about the halting problem and undecidability from the halting problem. These two proofs are so simple and basic that every student can understand and should be able to tell them if you meet someone on the street or your relatives ask, what have you learned at KAIST? You should be able to just stand up and demonstrate them why there are infinitely many primes, what is the halting problem, and why the halting problem is undecidable. Because it really requires no background knowledge and can be explained to everybody. And last time, I repeated this proof of the undecidability of the halting problem, and I reminded you of what the halting problem is. So let me fire up the slides. We're in chapter 2 about asymptotic unconventional computing, and I've reminded you of the halting problem and of its undecidability. Today we're going to continue discussing approximating the halting problem, but the halting problem is such an important problem with practical relevance that in the rest of this chapter we'll be trying to devise unconventional approaches to solve the halting problem, which is undecidable to a Turing machine. But maybe to other type of machine it can be decided, such as, for example, to Zeno machines. And in particular, we're going to try to realize Zeno machines using Einstein's theory of general relativity, actually. Then we're going to characterize the computational power of such Zeno machines in terms of revising computation. Technically, this is a topic of the famous Schoenfeld lemma. Then we will discuss other methods of asymptotic computing, such as mechanical computing and optical computing. And we will also talk about analog Zeno machines for analog computer, but analog computer will be the topic of chapter 3. So that's already a cliffhanger for chapter 3. So let me skip over the slides of undecidability of the halting problem. First, we covered that extensively last time. Let me just remind you, what is the halting problem and how is it formalized? So informally, the halting problem is the following question. Given an algorithm, source code, or otherwise encoded as an integer, as a natural number, and given an input x to that algorithm. Now, thought experiment hypothetically, if we were to execute that algorithm on that particular input, will it terminate or not? And remember that simulating that algorithm will reveal, in case the algorithm does terminate, namely simulating until the simulation reaches the end instruction. But in case the algorithm does not terminate, then the simulation will never know and will never be able to stop until this algorithm doesn't terminate. And we're not counting heuristics that simulate the algorithm for 1,000 or million or billion steps and then give up, because maybe the algorithm does terminate after 1,000,000,005 steps, in which case we have given up too early. So that would be a heuristic, and that's not what we're interested in. Now here we consider the halting problem as a subset of natural numbers, which means that the algorithm is considered encoded as a natural number. Could be a huge natural number. If you have a source code, then each symbol in the source code is maybe 8 bits long. And if your source code is 100 symbols long, then it is 800 bits long. And interpreting these 800 bits as a very long integer in binary means encoding this algorithm as a natural number. Same for the input to that natural number. And the angle brackets indicate that we combine the two integers, maybe by interleaving the bits, one bit from the first, one bit from the second, second bit from the first, second bit from the second, and so on. In this way, this pair, algorithm as a natural number and input as a natural number, are combined into one much larger, possibly natural number. And formally, as a decision problem means, given the natural number, answer whether that natural number belongs to that set or not. So every subset of natural numbers amounts to a decision problem. And this is a particularly important decision problem. And this, whether the halting problem is decidable or not, amounts to the question whether there exists an algorithm which on input of such a pair, algorithm and natural number, different algorithm, does that algorithm exist which always stops and always answers correctly whether the input natural number belongs to H or not, whether the algorithm A on input X terminates or not. And our proof showed, or Turing's proof showed, that this is not the case. There does not exist such an algorithm. Now let's consider some variants of the halting problem. First, we're going to consider a one-sided variant. A variant where we only need to answer yes. In the positive case, when the algorithm A on input X does terminate. When algorithm A on input X does not terminate, then we don't need to answer. We may answer no, or we may answer not at all. And in particular, we may keep computing. That's a relaxation of the original common requirement for deciding a problem, always answering always correctly. So here's the relaxation. Stop with answer yes in the positive case, and don't answer and possibly don't even stop in the negative case. This relaxation is possible. There exists such an algorithm, and we already saw that. It's simply simulating the algorithm A on input X has exactly this behavior. So this is possible. Next, we're going to consider the opposite relaxation. Namely, in this case, we're supposed to answer no in the negative case, and we don't need to answer, and we may even continue computing indefinitely in the positive case. So that's kind of the role switched compared to here. This is not possible, this relaxation. So this means that really the difficult part of the halting problem is not the positive part saying yes, that's possible. The difficult part is saying no, the negative cases, identifying the negative case within a finite number computation time. Now, how about other ways of relaxing the decision problem? So here we always require that the answer always occurs and is always correct. Now let's relax it to say that there must always be given an answer, but it needs to be correct only finitely often. Okay, not always, but finitely often. Let's say maybe 1,000 times the correct answer. We don't care about the other cases. This is possible. And actually, this is what most heuristics do. They give correct answer finitely often and an incorrect answer infinitely often. Now let's make the relaxation a little bit more strict by requiring that still the answer must be given always, but it needs to be correct not just finitely often, but infinitely often. Notice that we have infinitely possible inputs, right? Every natural number amounts to an input, and answering correctly on finitely many, that's what we just saw, but answering correctly infinitely often, that is also possible. Why is that possible? It's actually pretty simple. Consider an algorithm which always answers yes, always answers on input of this algorithm A and input X, it terminates. So imagine an algorithm which doesn't even simulate or look at the input A and X, but simply says, yes, it terminates. This algorithm will give the correct answer infinitely often because there are infinitely many algorithms which terminate. And for these, the answer will be correct. And for the others, it will, of course, be incorrect, but that's not what we worry about. It is infinitely often the correct answer. Notice that there are still infinitely many incorrect answers, right? Because the natural numbers are infinite, there can be infinitely many correct answers and infinitely many incorrect answers. So this relaxation, which is even stronger than the previous one, finitely often, infinitely often, is still possible, and it's possible trivially so. Yeah, we devised an algorithm which doesn't even process its input, it just simply says yes, and it will be correct infinitely often. So that's not very interesting. So now we need to step up our game a little bit further and make the relaxation even more strict. Always stop and answer, but now we require the answer to be incorrect only finitely often. We call that the algorithm solving the relaxation 5, Roman 5, would give the correct answer infinitely often, but also would give the incorrect answer infinitely often. And now we require that the incorrect answer must be given only finitely often. And this turns out to be impossible also. I'm not going to repeat the proof. It's a simple proof, and I would refer you to my lecture CS422, Theory of Computation, Shameless Cross Promotion. So that means, in a very strict formal sense, the halting problem cannot even be approximated well. Now, why is the halting problem so important? Because all these considerations not only apply to the halting problem, but to any non-trivial so-called Markov property of a given program. The halting problem is one non-trivial Markov property, namely the question whether the program terminates or not, and any other non-trivial Markov property, for example, whether a certain line in the source code of the program will ever get executed, or whether it's simply a redundant command in the source code. It's another non-trivial Markov property, and this is also undecidable by Rice theorem. And this seriously limits all scientific approaches to software verification, because it means that the only thing we can do to really perform software verification rigorously can only be done using heuristics. Now, of course, heuristics are important, an important part of engineering, but scientifically speaking, particularly referring to theoretical computer science, it is impossible to rigorously do software verification always correctly. These are the two requirements here. So now let's relax these conditions by considering algorithms which not necessarily stop always. But first, let's talk about accelerating so-called Zeno machines. So recall Moore's law about acceleration of computing power. Every 2 years, the computing power of digital computers used to double, and maybe it will continue doubling. Maybe it will continue doubling using advanced methods, parallel computing, optical computing, DNA computing, quantum computing. And that's an example of accelerating computation. What can we do taking into account accelerating computation? So far, we've always considered buying a computer and then running a program, for example, a program trying to solve the halting problem on that computer. But taking into account that computing technology is accelerating, we could keep running our algorithm or program for maybe 2 years and then suspend it, hibernate it, store its current execution state on a hard disk, and buy a newer model. After 2 years, there's a new model which is twice as fast according to Moore's law. And we could then wake up our hibernated algorithm on the new, faster computer and have it continue running on the faster computer, harnessing the acceleration of technology that has taken place while the algorithm had been running for the first 2 years and then running for another 2 years at twice the speed, and then do the same over again. Hibernate the progress state of our executing program, transfer it to a new model of computer, which again runs at twice the speed, so it's already 4 times the speed. So that means our program keeps running faster and faster because it is run on faster and faster computers, not starting from scratch, but continuing where it has previously left off. And remember, this is similar to Zenon's paradox, right? What again was Zeno's paradox? Zeno's paradox from Greek mythology is the paradox that the fastest runner arguably could never overtake the slow tortoise. Because if the tortoise gets a head start, maybe like 10 meters head start, when the fastest runner in the world has caught up with the tortoise, has caught up with the head start 10 meters, during that time, the tortoise has moved on, maybe only 1 meter. And when the fastest runner in the world finally has caught up with this 1 meter, during that time, the tortoise has kept moving on, maybe 10 centimeters, and so on. So this is the finest paradox, which argues that the fastest runner cannot ever catch up with the tortoise. But of course, this is no paradox at all, because the time steps which it takes to catch up with a head start, first 10 meters, then another to catch up with 1 meter, and then another to catch up with 10 centimeters, these time steps become shorter and shorter. And they add up, and although it's infinitely many time intervals, because the time intervals become shorter and shorter, they add up to a finite time when the runner has actually caught up with the tortoise and is on the same as far on the racetrack as is the tortoise. So mathematically, this simply amounts to a geometric series with infinitely many terms, but since every term becomes smaller and smaller, adding up these infinitely many terms amounts to a finite number when it has caught up. So it's infinitely many steps, but since the time allotted for each step becomes smaller and smaller, they add up to some finite time. And if we only allow for finitely many iterations, then this amounts to asymptotically infinitely many steps made by the fastest runner. Otherwise, it's infinitely many iterations of catching up. And the same applies to our accelerating computation, right? So during each new iteration, it takes shorter time for our algorithm to progress. So now imagine that a stronger Moore's law, where not only does the computing power, computers become twice as fast every 2 years, but even it accelerates further so that it takes less and less time for the next generation with double running time to appear. Maybe in the next iteration, it takes only 1 year for a twice as fast computer to appear. Then it takes only half a year for a twice fast computer to appear, then a quarter of a year, and so on. So in this way, accelerating computation by regularly proceeding to a faster computer allows to execute an infinite number of computational steps in bounded time. Is this realistic or not? Well, honestly, this is unrealistic, but recall the question of what is realistic or not is a very subtle one. It's a matter of approximation. Remember that also your current computer only approximates a Turing machine. with its infinite tape, because it has a very large but finite storage. And similarly, with accelerating computing technology, one will probably never be able to do infinitely many computational steps in finite time. But as an approximation, the number of steps that can be done within a year will increase over time, and thus, in an approximate sense, in an asymptotic sense, one can arguably that such a Zeno machine can make at least approximately infinitely many steps in finite times. That's the essence of Zeno machines. A Zeno machine can make infinitely many steps in bounded time by, for example, accelerating computation. Such machines don't exist, but Turing machines also don't exist. Your PC is an approximation of a Turing machine, and accelerating computation and engineering capabilities are an approximation to Zeno machines. Now let's look at a possible way of actually building Zeno machines, possibly in the future. And this is using relativistic computation. You may remember relativity theory from Albert Einstein about what happens when something moves very fast, approaching a velocity, the speed of light. Again, the speed of light itself is not attainable, but asymptotically, one can get closer and closer to the speed of light. And that's when space-time starts deviating from classical Newtonian and Cartesian space-time. Maybe there's a time difference happening between the clock of the observer, who is in rest, and the clock of the moving particle. And this is very important. For example, your GPS must take that into account, correcting factors, because, for example, the satellites that provide the GPS signal move in the gravitational force of the Earth, and gravitation equals acceleration according to Einstein, and that affects the running time of the clock. The clock in the satellites moves at a different speed than our clock who are resting on the surface of the Earth. And a very famous confirmation of this prediction of Einstein, right? Einstein predicted this in like 1905, right? Yeah, the miracle year of Einstein, where he wrote several papers. He didn't get, by the way, he didn't receive the Nobel Prize for this. The Nobel Prize was received for his explanation of the electro light effect. But anyway, so it took several decades to actually confirm Einstein's prediction. People were suspicious about his theory of relativity. Also, yeah, there was a lot of anti-Semitic propaganda against his theory, but very famous experiment that actually students of physics can and should reproduce nowadays. For example, in the Center for High Energy Physics is about muon. Muons are particles that resemble electrons, but they are much heavier and they have a much shorter half-life time. So a muon's half-life time is roughly 1.5 microseconds, not milliseconds, but microseconds. So 1.5 microseconds may seem like a short time from our human perspective, but remember, that the clock rate of Apple II computer or Commodore 64 used to be 1 megahertz, which means that every clock cycle was 1 microsecond, and the half-life time of a neuron is 1.5 clock cycles. And nowadays, computers are easily 4,000 times faster. So for nowadays computers, 1.5 microsecond computer can perform like easily 2,000 or 3,000 instructions during this half-life time of a neuron. And after this half-life time has expired, a neuron kind of, in a sense, breaks up, evaporates into photons, light being emitted. And half-life time means that it's not deterministic. It's not like a neuron gets created and then after exactly 1.5 microsecond it blows up, but it's statistically, that's the average time for it to live. Now, neurons are created in our Earth's atmosphere when high energy particles like gamma rays enter our atmosphere, and then neurons travel towards the ground. Of course, that's the direction where the high energy particle came in to begin with. But in order to reach the ground, even at a velocity which is very close to the speed of light, 98% of the speed of light, the time it takes for a neuron to reach the ground, so they're created at 10 kilometers height, and at its velocity, only a very small fraction will still be alive because it takes too long for them to proceed down. So you can do the calculation. So the time for a muon to make up this distance exceeds this half-life time by a large factor. So only 0.3 out of a million muons should end up arriving at the surface of the Earth. Now, if you do a measurement at 10 kilometer height, maybe using some balloons, and then you do the measurement here on the ground, turns out that many more muons arrive actually at the surface of the Earth. Many more than only 0.3 out of a million, maybe about 50,000 out of a million. So that's about 4.9% make it towards the ground. How is that possible? And that's the confirmation of Einstein's theory of relativity, which says that for the muon traveling so fast, its internal clock proceeds slower than for us who are at rest on the ground. This is called time dilation. So the internal clock of the muon runs slower, much slower. And a different perspective is saying that for the muon's perspective, the distance becomes shorter because it travels so fast. So the muon sees a distance which is contracted, or the muon's clock is time dilated, it runs slower. It runs slower than our clock. And here's some calculations from the two perspectives. The non-relativistic, the incorrect one, says it takes 34 microseconds for muon to travel the 10 kilometers from where it was created at the border of the atmosphere to the ground. And during this 34 microseconds, which is much more than its half-life time, most of them would perish. But relativistically, for the muon, it's the time it takes to travel that distance is only 6.8 seconds according to its local clock according to time dilation, or put differently, it's to the moon, it seems like the distance is only 2 kilometers, whereas for us, for resting observers, the distance is 10 kilometers. So this is a well known and documented effect confirming Einstein's theory of special relativity. And now let's try to harness that in order to create a relativistic Zeno machine, a computing device which can make infinitely many steps in finite time by running faster and faster, like the Zeno's paradox, like the runner in ancient Greek mythology. And to this end, recall that every mass, according to general relativity, creates an acceleration, distorts space-time. Our Earth distorts it only a little bit. The Sun, which is much heavier, distorts it already noticeably. A neutron star distorts it even further, but ultimately, a black hole creates a singularity in space-time. And here you see what happens when an object falls into such a black hole. The distorted space-time results in the internal clock of that falling object falling into that singularity to proceed slower and slower time dilation. Whereas for us as an outside observer, our clock continues moving at a different rate. Or put differently, from the perspective of the object falling into the black hole, it doesn't notice that its clock is running slower. For the object falling into the black hole, it seems like the outside observer's clock keeps running faster and faster. So here, the object has already moved considerably into the singularity, although it's still not in. Its clock runs slower. The outside clock keeps running at the same rate, or vice versa, principle of relativity. For the object falling into the black hole, its clock keeps running at the same pace, and the outside observer's clock keeps accelerating. Accelerating, remember, we want to realize an accelerating computation. And as the object falls, it keeps falling into the black hole. When it reaches the event horizon, to the outside observer, it seems like its clock freezes, goes slower and slower, and then eventually stalls. Or vice versa, for the object falling into the black hole, it seems like the outside observer's clock has kept accelerating faster and faster, and now the outsider's clock is ticking at an infinite pace. And that's what we want to use, right? So this is what we try to realize a Zeno machine, namely, we put the computer with termination we want to decide, computer which is supposed to make infinitely many steps outside to the outside observer, outside of the black hole. And we ourselves jump into the black hole. And then we, in finite amount of time, according to our local clock, can observe infinitely many instructions being executed by the computer outside of the black hole. Now, is this practical? Well, there are some downsides to this approach because although we might now know whether this computer terminates, we might know the answer to the halting problem, but we don't have much benefit from it, right? After all, we are falling into the black hole. and we're getting squished to death. So it seems possible to realize xenomachines making an infinite number of computational steps through accelerating computation using Einstein's theory of general relativity, but it is not really practical. So therefore, let's continue trying to find other ways of performing asymptotic computation. Asymptotic means making something infinite as an approximation to something that can be realized as being very, very large, although finite, like Turing machine being an asymptotic version of your PC with its memory being considered infinite, although your PC's memory is finite but very, very large. And similarly, a Xeno machine being able to make maybe very many steps before being rescued from falling into the black hole, although not technically infinitely many steps. And next, we want to explore the actual computational power of such a Xeno machine, regardless of whether it can be realized or not. Similarly, as computability theory and complexity theory investigate the capabilities and limitations of Turing machines, including undecidability of the halting problem and including P versus NP problem, regardless of whether a Turing machine can be realized or not using your PC or not. So this is the next part in our chapter 2 on asymptotic computation. What is the computational power of a Xeno machine? Abstractly, some computer which can make an infinite number of steps, regardless of whether it can be realized or not. And to this end, we're going to relax and change our conception about computation. So previously, we always had the requirement that computation must actually terminate, right? Terminate, give an answer, and terminate. So all these conditions here, even the relaxed ones, would require that the computation stops and gives a correct answer, one-sided positive, one-sided negative, always correct was impossible, infinitely often correct was possible, only finitely often incorrect was impossible, but always about terminating computation. And now we're going to consider revising computation, which means we're going to drop the condition that the computation must stop. It must still produce an answer. That means now we consider algorithms which produce output, but which don't need to stop. And this is where I make a short break for you to digest that and to ask some questions and have some maybe discussion about the Xeno machines and about relativistic Xeno machines or other kind of accelerating computation. So I'm going to stop the recording. So now I'm going to continue recording and we move on to discuss the capabilities of revising computation, algorithms which don't stop, but which could produce output. Now it turns out that considering such algorithms requires some care. Maybe let me illustrate that. Suppose you run an algorithm which is going to give an answer to a decision problem. So it's going to say yes, or it's going to say no. And the algorithm may produce output, but it may change its mind. It may possibly revise its output. And to illustrate that, suppose you see the following on your terminal appearing. So you see yes appearing, which suggests that the answer to the decision problem, any kind of decision problem, could be the halting problem or any other kind of decision problem, suggests that the algorithm that has arrived at the answer yes. But since the algorithm keeps running, right? The algorithm doesn't stop, but produces output. Next, you see this. And the next thing you notice is the algorithm writing no. But remember, the algorithm still keeps running. It's a non-stopping algorithm which produces output. And the next thing you see is maybe the algorithm deleting its own output so far. And now what can you tell? What do you know? What can you take home from the algorithm producing this output? Maybe the next thing you know, it writes yes again, or maybe it writes no again. So the answer provided by such an algorithm is ambiguous. And such ambiguity didn't arise so far when we considered terminating algorithms. If an algorithm finally stops, then there's going to be the output that is then visible on the screen. That's the final output, right? It could have revised its output repeatedly, but once the algorithm stops, that's the final answer. When we now relax and consider non-stopping algorithms, we need to be careful to allow only a certain class of algorithms. For example, we would not accept an algorithm which keeps changing its mind all the time, saying yes, then deleting and saying no, then deleting, saying yes again, and then deleting and saying no again, all the time, flipping back and forth. Such an algorithm will not be, we will not allow such an algorithm, even under our relaxed assumption that we have non-terminating algorithm which produces output. And such an algorithm which keeps changing its mind is actually similar in philosophy to a thought experiment which is known as Thomson's lamp. Thomson's lamp is a lamp which keeps switching on and off faster and faster. So maybe like Zeno's paradox, and maybe like our algorithm, accelerating algorithm, which keeps changing its mind back and forth infinitely often. So Thomson's lamp is well known under this name, is switched on for 1 second, then it is here, then it is switched off for half a second, then switched on for a quarter of a second, then switched off for an eighth of a second, on again for a 16th of a second, and so on. Switched on and off and on and off, faster and faster. And the question is, after 2 seconds, at 2 seconds, is Thomson's lamp switched on or is it switched off? Now, again, that's of course a paradoxical question, right? There's no right answer to that. And that's exactly the problem we're facing here. When allowing revising computation, we need to prevent our algorithm from changing his mind infinitely often. Mhm. So yeah, again, observe the similarity to Zeno's paradox. However, Zeno's paradox is maybe slightly different in that Zeno doesn't keep changing his mind. He keeps on running at the same pace for shorter and shorter uh, distances using less and less shorter and shorter time intervals. But eventually, Zeno arrives, right? But our algorithm may keep changing its mind, and we need to prevent that. We need to define how often do we allow our algorithm to change its mind. So this is slightly different from Zeno's paradox, and possible choices is to allow our algorithm to change its mind, to revise its output precisely once, or at most once, meaning 0 or 1, allowing to change its mind maybe even twice, more general, precisely twice, or at most twice. 3 times precisely, or 3 times at most. Or maybe more generously, finitely often, arbitrary but finite number, but definitely not infinitely often, because infinitely often is not, yeah, it's not well defined. It's like Thomson's lamps. Is it a status? Is it on or off at 2 seconds? That question doesn't make sense. Similarly, question what is the algorithm's output after infinitely often changing its mind doesn't make sense. That's a nonsensical question. What also doesn't make sense is to allow it to change its mind precisely once. That's maybe a little bit more subtle. Why is that not helpful? Well, we can define it, but an algorithm which can change its mind precisely once is not any more powerful than an algorithm which stops. Why is that the case? Well, we can simulate the non-stopping algorithm, wait for its output, continue simulating it, waiting for its output to be revised once, and then terminating, aborting the computation. Because if we consider non-terminating algorithm, which allows its output to be revised precisely once, then once the one revision has happened, then we can safely abort it and thus make it equivalent to our classical terminating algorithms. So allowing an algorithm to revise its output precisely once makes sense mathematically, but it doesn't make it any more powerful than our previous conventional algorithm. We want to talk about unconventional computation, namely about revising computation. Notice that this is not the case if we allow an algorithm to revise its output at most once, because at most once means it could or it could not revise at all. So an algorithm which may revise its output at most once, we cannot just simulate and wait for the one revision and then stop it, because the one revision may never happen in case it makes only 0 revisions, none. So an algorithm which may revise its output at most once is already more powerful than an algorithm which may revise its output precisely once. Similarly, an algorithm which is allowed to revise its output precisely twice is not more powerful, because we can simulate it and wait for its second revision and abort it, thus arriving back at our conventional algorithm. So the real powerful revising computation is which allows to revise its output at most once, or at most twice, or at most 3 times, not precisely once or twice or 3 times. And more generally, allowed to revise its output an arbitrary unknown finite number of times. That's an important subtle point about condition F. Finitely often is different from at most once or at most twice or at most 15 times because the number is not known. Whereas when we allow the algorithm to revise its output at most 15 times, then it's 15. And to illustrate the power of an algorithm which may revise its output at most once, observe that such an algorithm can solve the halting problem. How can such a revising algorithm solve the halting problem? Well, recall our simulation, right? Our simulation is able to answer yes correctly, but it cannot answer no safely because the algorithm might terminate after 1 more hour. But a revising algorithm could just first answer no and then start simulating on and on and on. And if the simulation terminates, then it will revise its output no and replace it with output yes. And recall that the simulation, when it says yes, it is correct. Whereas if the simulation never terminates, then it has already output no initially, and then will be the correct answer. Let me say that again. An algorithm which may revise its output at most once can solve the halting problem. By first writing no, then starting the simulation, and if the simulation stops, then revise its answer no from no to yes. Otherwise, keep simulating and keep showing the initially written answer no until the end of time. This already illustrates the power of non-terminating algorithm with revising output. Notice that such a revising algorithm can also solve the complement of the halting problem. Simply by flipping its answer. It first writes yes, and then starts the simulation, and if the simulation terminates, then it revises its output from yes to no. In fact, revising computation with at most 1 revision is closed under complement. Same for revising computation with twice revision. Being allowed to make at most twice revisions is of course even more powerful than being allowed at most 1 revision. Making precisely twice revision is not more powerful than making precisely 1 revision, but making at most twice revisions is strictly more powerful than making at most 1 revision. And this is exactly the content of Schoenfield's lemma. Joseph Schoenfield has characterized in a mathematical theorem. Historically, it's called a lemma, but I think should deserve to be called a theorem. Characterized the computational power of a non-stopping algorithm which is allowed to revise its output at most k times. Not precisely k times, but at most k times. And Schoenfield has proven that this is equivalent to a conventional algorithm, a stopping algorithm, which is allowed to make k queries to the halting problem as an oracle. Now, oracle computation and oracle Turing machines is arguably an unconventional model of computation, which was introduced by Alan Turing in his PhD thesis. And we will talk about that, can learn much more about that in my course CS422, Theory of Computation. But for now, I want to leave it here. Just the beauty of this famous Schoenfeld lemma characterizing the computational power of algorithms which don't stop and which may revise their output at most k times. Now, this includes the case where k is an arbitrary finite number here, the last case. That's simply an algorithm allowed to make any finite number of queries. Okay. And Schoenfeld, Joseph Schoenfeld, was a famous logician, and he wrote a very good introductory textbook on mathematical logic. And I recommend this to any student of mathematics because this book is so easily accessible. So any student of mathematics will have no problem in studying logic by him or herself simply by reading through this book. And it's famously said that many nowadays logicians have become logicians by and after having read this book. So that's a little bit promotion of mathematical logic and of Joseph Schoenfeld. And since we're running out of time, let me end here and give you an indication of what we'll do next week. So next week, we were going to consider two other ways of asymptotic computation, making somehow computation involving infinity in some sense or another, not like in a Turing machine, which has infinite memory, not like in a Zeno machine, which can make infinitely many steps as an approximation to actual computer, but machines which can somehow use infinity in different ways, mechanically or using optics. That's our plan for the rest of chapter 2. And then we're going to start with chapter 3 about analog computing. So that's all for now. That's all for today. Remember that next Friday, we're going to have the one-on-one sessions where you're asked to present your progress, reading the assigned chapter in the book on unconventional computing, and also show me your outline of your talk, 3 to 6 sub-chapters, subheadings of your upcoming presentation. Thank you very much for attending. And if you are participating in Kai's Post-Ex Science War, then all the best luck with that. Then otherwise, have a great weekend, and let's see you next week on Thursday. Goodbye.